All right, welcome back. So today we are going to be continuing our conversation about solving systems of linear equations. So far, we've discussed how to solve these systems by the graphing method, the substitution method, and the elimination method. Today, we're going to be bringing them all together, and we're going to be talking about special cases. Let's think back to when we were solving equations in one variable, right? We had three different types of situations. We could have a one solution where like x could be equal to 2. We could have a no solution, or we could have an all real numbers. And that's the same case here for systems of equations. And today we're going to be talking about what happens if we have those special cases. So again, let's think back. When solving equations in one variable, it is possible to have a one solution, a no solution, or an infinitely many solutions. The same results can occur when graphing or solving systems of equations. So let's just talk about equations in one variable just to give us a quick refresher. So let's say we have this equation here and we want to solve for x. 2x plus 4 is equal to 2 times x plus 3. We want to simplify both sides first. So we get 2x plus 4 is equal to 2x plus 6. We want to get our x terms to one side and our constants to the other, but if we think back, a good old Q-tip was we want to move our variables first. In doing so, we're going to see that our x cancels out. We have 4 is equal to 6. We know this is not true, so we would call this a no solution. But what if we had a case that looks like so? 3x plus 5 is equal to 5 plus 3x. Well, just like we did before, we're going to want to bring our variables to one side and then get our constants on the other. So we end up with 5 is equal to 5. In the past, we've said that we could have an all real numbers answer for this because it's a true statement. Our variables canceled out. 5 is equal to 5, so we would write all real numbers. We also could have an infinitely many solutions answer, and that's the same thing as all real numbers. But today, since we're talking about solutions of systems, we're going to try to move forward with infinitely many solutions. So just for the time being, I'm just going to abbreviate IMS. So this should be a good refresher as to solving equations in one variable and having those special cases. And today we're going to be talking about solving systems to get those special cases. So the first example that's on your guided notes is this system here. 4x plus 2y is equal to 2, and 2x plus y is equal to 4. Now we have three different methods that we can use to solve a system. We can use the graphing method, substitution method, or the elimination method. In this example, we're going to use the elimination method, and we're going to try to eliminate the x terms. So in order for us to eliminate these x terms, we have to multiply that bottom equation by -2. The reason we're multiplying that bottom equation by -2 is because we want to have the opposite of 4x, which is -4x. And multiplying the current term of 2x by -2 yields us that -4x. So we end up with the system pictured right here. 4x plus 2y is equal to 2, and -4x minus 2y is equal to -8. And now we can add vertically. So our x variables cancel out, but also our y variables cancel out. So we end up with 0 is equal to -6. Is that a true statement? Is 0 equal to -6? No way, Jose. So this is technically what we call a contradiction. So that means that there is no solution for it. And if we were to use the graphing method for it, it would look like such. It would look like so. Graphing these systems shows that these are what we call parallel lines. They will never intersect, so there can't be a solution because they're never going to have a point of intersection. Since we know parallel lines have the same slope and they never intersect, there is never going to be a solution between these two equations. If we end up with a situation of having parallel lines or having a no solution, that's because they're never going to intersect. We ended up with that false statement. We ended up with this 0 is equal to -6, and we know that's not true. So that's going to be a no solution, which piggybacks off of what we were solving when it came to equations in one variable. Let's talk about this system here as the second example. The system provided is y equals 4 minus 3x, and 3x plus y is equal to 4. So again, we have three different methods that we can use to solve this system. We have the graphing method, substitution method, and the elimination method. But because the first equation is already solved for a variable, we're going to want to use substitution. We have that y is equal to 4 minus 3x. So in the other equation, we're going to substitute y for 4 minus 3x because that's what it's equal to. When we substitute, we get 0 plus 4 is equal to 4, and 4 is equal to 4. So in this instance, we get a true solution. We got 4 is equal to 4. Because it's a true solution, the equation is what we call infinitely many solutions. This system represents a solution of infinitely many solutions. And here's why. If we were to graph it, the slopes and the y-intercepts are the same. These end up being the same exact line. If I were to go back up in our original and rearrange the bottom equation, 3x plus y equals 4, I would have to subtract 3x on both sides, and we get y is equal to 4 minus 3x, which is the same exact equation as up top. That is a horribly drawn y. Let's try that one more time. There we go, that's better. So you get y is equal to 4 minus 3x, which is the exact same equation as up top. So it would make sense that when we graph it, it's the same line because it's the same equation. So the same equation represents, well, the same line. And this happened because we had infinitely many solutions. We ended up with a true statement. So they're not going to have a one solution. There's going to be infinitely many of them because they are the exact same line and they intersect at every single possible value of x and y. Awesome. With this, please work on problems 1 through 3 on the guided notes and resume when you're ready to move on. All right, so in here, for this slide, what I made was a table for you to identify how many solutions there are going to be from a couple of different characteristics. So we're not going to go through the inconsistent, dependent terminology that your guided notes provide you. We're just going to talk about how to find the number of solutions, give you an example and a graph of each type. So if we have a one solution example, if we're looking at the slope and the y-intercept, if we are comparing the slope and the y-intercept, well, they're going to have a different slope and a different y-intercept. And if we look at them from a graph, they're going to have one point of intersection. They're going to hit at that one spot where those two lines intersect. And this is what we're used to seeing. And one possible example could be y equals x plus 3 and y equals negative x plus 6. Notice they have a different slope and they have a different y-intercept. But now we're talking about special cases. So if we're talking about a no solution situation, they're going to have the same slope, but they're going to have a different y-intercept. And the reason they have the same slope is because they're going to be parallel lines. They're never going to intersect. And they have to have a different y-intercept because if they had the same y-intercept, then it'd be the exact same equation, the exact same line. And in the graph, again, it's showing you a representation of parallel lines. Those lines are never going to intersect. They have the same slope. And one possible example of a system would be y equals 2x plus 5 and y equals 2x plus 2. Notice again, they have the same exact slope, but a different y-intercept. So they have the same slope, 2x and 2x, but they have a different y-intercept of 5 and 2. Now we have one more situation, infinitely many solutions. When we are looking at that, they're going to have the exact same slope and they're going to have the same y-intercept. And that's because they're the exact same equation. They're the exact same line on a graph. So notice in the graph example, there's only one line shown because they're the same line. If we look at the example of a system, the top equation is in slope-intercept form, the bottom is not. But if we were to rearrange and solve for y, we're going to find that it has the same slope of 3x, and it's going to have the same y-intercept of 4. So with this in mind, please try out the rest of the guided note problems, identifying how many solutions there are, and then figuring out what the solution is if it is a one solution. Again, you can disregard the terminology of dependent and independent and consistent and inconsistent. We aren't going to go in depth with that. It's more important that we're able to identify how many solutions a system is going to have before we tackle the system itself. Great job with this, folks. You're working really hard. You should be really proud of yourself. I know I am of you, but you should take pride in this because you're doing really, really well. If you have any questions, please do not hesitate to let me know, and I will talk to you soon. Thanks.